So that was resonance happening in a column of air. When the note that I played on the phone matched the natural frequency for that particular length of air, we got resonance. I was just simply able to adjust the length of air till it was the correct length for the particular note. And there were a couple of positions, just like in the vibrating spring. If you remember back in the previous video, we had a string which I had a little motor, and the motor was able to vibrate the string. And you can see there's a pattern on it. This, of course, is a transverse wave. Strings can vibrate with transverse waves. Springs can also vibrate that way, but the way I was using it in the previous example was a longitudinal wave, which is the only way that air can vibrate. And by the way, we know that because light is a transverse wave as well. It can be polarized. Remember we talked about polarized light and polarized glasses. Sound cannot be polarized. So if you're asked how do we know that sound is a longitudinal wave, it is the fact that it cannot be polarized. Okay, on my video here we can see we're getting different patterns of vibration on the string, different positions of nodes. We'll go back there a little bit on it, and again this is just to remind you of that. So you can see if I pause that, there's 1, 2, 3, 4, 5 nodes there, and I adjusted. Now I'm not even seeing the full length of the string, it's just a quick demonstration. Now we're reducing the frequency somewhat. We've about 3 nodes there, and so on, and a few more. So different frequencies, different vibrations occurring. So these would all be harmonics of the simplest frequency. Now that is there just one node in the middle, and this would be the second harmonic. So again, you can look at diagrams in the book for vibration. We're just showing that strings can also resonate at particular frequencies. But it's not just strings and springs and things like that. We also get resonance in other objects. Okay, this is a video of a bridge. Right, this is the Tacoma Narrows Bridge in America. When they built this bridge, they didn't take into account the wind coming down the valley, and it came at a particular frequency or gust that had set up resonance. And as you can see, the bridge became somewhat unstable. Hopefully this won't happen with the New Ross Bridge. And again, eventually it actually collapsed. So this was a design flaw in that they hadn't taken into account resonance. Resonance was occurring because of the air currents swept down the valley, caused, just like when you blow over a tin whistle, there's vibrations in it, and it can get the air in the tin whistle to resonate. Here, the vibrations in the wind coming down the valley got the whole bridge to resonate, and eventually after a few days it collapsed. Something similar to this happened with the Millennium Bridge in London, but there it was due to people walking in step across it, and they had to change its natural frequency by putting weights on it. So resonance is very important in engineering. Okay, let's just go back to your own book. Right, bottom right here of the page, you can see here examples of resonance. Somebody pushing a swing. If you push at the right time, the swing will get going and get higher. If you push incorrectly, it won't. The story of the opera singer causing a glass to shatter. Well, wine glass and things have a certain note. When you tap them, you hear it ringing at its natural frequency. If you were singing at that note, you could transfer energy sufficient to cause it to break. Barton's pendulums are a bit like the example I showed in the animation. When you set these vibrating, the frequencies will transfer between objects that have the same natural frequency. Okay, and there are links in your own book to videos and things like that, so use the online resources there to look at these. So your vocal cords, of course, resonance in your voice box, that's important too. And you can detect, as it says here, a sound level meter can be used to detect sound intensity, so that just might be asked as well. And finally then, in this chapter, we will look at vibrations in stretched strings and in columns of air. The sonometer is a device you'll use in an experiment to see how the frequency of a string depends on length. But we will be using the formula, which we will see. So, at its fundamental frequency, a vibrating string has an antinode at center and one node at each end. So what does that mean? Well, just looking at that definition. So a string will vibrate at its fundamental frequency, something like that. So an antinode is where there's the most displacement there, and nodes at either end. So that's the way a guitar string has to vibrate at its simplest, but of course it can have the harmonics as well. And that's what your book shows here. Bottom of page 198. There's the diagram, better than mine, showing the possible vibrations of the string, something like you saw in the video there. And so there's the fundamental, the second harmonic, the third harmonic, the fourth harmonic, the fifth harmonic. So these are all multiples of the fundamental frequencies. So if you knew the frequency, you just multiply by 2, 3, 4, 5 to find the frequencies, and all of those can be there at the same time, causing sound. The key formula for the frequency of stretched string is up here on the top of the next page, and this one we will be using in calculations when we do them in class. What it shows, and it summarises all the other formulas that are on this page, it is in the log table, so you'll be able to look it up in an exam, but what it shows is that the frequency that a string vibrates at depends on 1 over 2 times its length multiplied by the square root of the tension over the mass per unit length. So L is the length of the string, right, one end to the other. T is the tension, how many newtons of tension are pulling on that string. It can be measured with a Newton balance, which you'll do in your experiment. Mu here is the mass per unit length. In other words, how many kilograms of mass are in 1 meter of that string. So that mass per unit length. So as you know, if you've played a guitar or something, some of the strings are thicker than others because they're a heavier mass, and that does affect the frequency. So what does the frequency depend on then? We can see the frequency will be inversely proportional to the length. Why? Because length is underneath here. Therefore, if this gets bigger, the fraction gets smaller, because if the number underneath the line gets bigger, the whole fraction is a smaller number. Therefore, the frequency will be smaller. So frequency inversely proportional to length. So we can also see how the frequency depends on tension. Well, tension is above the line, but it's behind the square root bracket. So the frequency depends on the square root of the tension. It is also depends inversely with the square root, of the mass per unit length. So 1 over square root of the mass per unit length. So we will be proving these two in an experiment. But if you double the length, you'll have the frequency. If you increase the tension by 4, you'll double the frequency. Why double? Well, if you increase it by 4, square root of 4 is 2, so you'll double the frequency. So that's how the frequency is affected by tension and length. And anyone playing guitar knows you can adjust the tension, but you can also adjust the length as you're playing by putting your finger on the different frets, and that adjusts the frequency too. So again, a lot of this links with music and sound. So that's the vibrations in a string. What about in a pipe? Well, we've already seen the vibrations in a pipe. I did those with the little experiment, but we also did them there with the spring. The spring shows what's happening in the pipe. So let's see what your book has on that. And it has these diagrams on the left showing the types of vibrations that you can get, and these are important. You can be asked to draw these in an exam. In open pipes you get all the harmonics, the first, the second, the third, the fourth, the fifth. In closed pipes you only get the odd, first, third, fifth. You do not get, and therefore the notes doesn't have as much note or sound quality different in open and closed pipes because of that. How do we draw? Well, let's just draw the first 3 possibilities for an open pipe. In an open pipe there has to be an antinode, that's a lot of vibration at the top and bottom. So this is the diagram we get. For the second position, and I'll draw it longer because it will be a longer length, again we must get the next possible position where we can get an antinode at top and bottom, and that would be this one. Right, so 2 there corresponds to the first, but now we've added on another length. And the next one again, beyond that, and really you just have to practice drawing these. There is no solution other than that. Now I've just squashed it a little bit up at the top, but there we go. So this corresponds to the second one, and there's the third one. So this here is the fundamental frequency that vibrates. You'll notice this is a distance of an antinode to antinode. So the length there is exactly half the wavelength. This is half, and here we have another half. This is exactly the wavelength, and this is the full wavelength and a half. So that's 3 halves, or 3/2. So basically we're getting each one is double the previous one. So this is double the so this is twice the fundamental, 3 times the fundamental wavelength. So in other words, this is frequency, the fundamental frequency, this is 2f, and this is 3f. Okay, and in your own book there, in a closed pipe the situation is different. So these you have to be able to draw and to recognize that the lengths correspond to half a wavelength, full wavelength, 2/3, 3/2, 1.5 wavelengths there. So 1.5 wavelengths for this one. Frequency will therefore be f, 2f, and 3f. For closed pipes, the conditions are different. Again, to hear a loud sound, there must be an antinode at the top, but now because it's closed at the bottom, there will be a node, no displacement at the bottom. Okay, so that's the first possible one, and that's a node to an antinode. That's exactly 1/4 of a wavelength of the full wave. The next possible position, and then I've probably drawn them a bit big here, would be this, and then in, and then up again. So, alright, so that's the next possible position that you can have. And that will correspond to, as we said, that's 1/4 of a wavelength, and then this here is a antinode to antinode, that's a half a wavelength, so that's 3/4 of a wave, right? And the final one, which I'm going to have to squash in a bit because we didn't give enough space, will look like this. Okay, so we have, this here corresponds to the second one, and then up again. So that's 3/4 and another half. So that's 3, 4, 5/4. 5/4 of a wavelength. So we have, this is the fundamental. This will be 3 times the fundamental because 3/4, and this is 5 times the original, so this will be 5 times the fundamental. You will only get the fundamental, 3 times the fundamental, 5 times the fundamental. You're getting the odd harmonics. And again, you have to be able to draw these diagrams and explain that. Again, your own book has it done there as well. But that's the situation with open and closed pipes. They do ask those diagrams to be drawn. So again, that's the main end of that chapter there, looking at the pipes. So let's just have a look. Yeah, that's all that's in the chapter. We've looked now at all the key things about the waves and sound. So again, just to recap, resonance, the transfer of energy between two bodies of same natural frequency. We know that sound is a wave because we got interference with that 2-speaker experiment. We know a little bit about the decibel scale and sound intensity levels. We know what sound intensity is. It's the amount of energy passing through 1 meter squared per second at right angles to the direction of motion of the sound wave. So look back at that. We saw as well then resonance occurring in open and closed pipes and also in strings, and being able to understand the difference between the fundamental frequency, the natural frequency that some object will vibrate at, and we also looked at then the multiples of that, the harmonics and the overtones. So the harmonics again, they are, the fundamental frequency is the first harmonic, the second harmonic is twice the fundamental, third harmonic 3 times the fundamental, and so on. Again, you have to look at the book to connect all of these bits together and have a look at some of the examples. There will be questions on this that we'll look at, and calculations. Questions and comments can go down below. I also put the links to the other little video on decibels down below, and so on. So you can also find other resources online. Okay, so that's it for the chapter here on vibration and sound. Go over it carefully and make sure you know the different definitions. Write out, draw out diagrams and definitions to help you remember. Have your own notes made of them. Okay, bye for now.